All right, so now let's look at the representations themselves. So these representations can be expressed in what are known as weight diagrams. So weight diagrams derive their name from the fact that, remember, so let's look at SU2. So suppose SU2, we take J to be 1. Does anyone remember how many states this irreducible representation should have? What about if I had J equals to half? What would be the dimension of J equals to half? Think of the electron.
Would be like plus minus half, right?
Yeah, so a little bit too, right? So what should be the same formula should give you this. How do you get this from this? 2 times this plus 1, right? So here you'll get 2 times J plus 1, 3. Right, so we have 2J plus 1 is the dimension of the Irreps of SU2. Remember? So let's look at J1, J equals to 1. And we had 3 states, 3 linearly independent states. One was M equals to 0, one M equals to plus 1, and one was M equals to minus 1. And the J's, J plus, took us in that direction. And, so they were, right? So J plus, and this was J minus, right? So this was the J equals to 1, right? And the fundamental representation was just 2, right? That's just M plus half and M minus half. J plus took us that way, J minus took us that way. So for SU3, the fundamental representation is 2-dimensional because we have 3 eigenvalues, 2 eigenvalues. So we can then plot these eigenvalues along the x-axis and the y-axis, or the y-axis and the x-axis. Sorry, this is not very good. And I3 is the eigenvalue corresponding to the lambda 3, and say I8 is that one. And then what happens is that we will have U3 of the fundamental representation has 3 states. And so that's Q, right? So Q, we can write this as Q1 U D S. U for up, D for down, S for strange. Okay, so this is the weight diagram for the fundamental representation. Okay. And the values are that this is plus half in some units, this is minus half, this is minus 1 over square root of 3, and this is 1 by 2 square root of 3. So the whole thing should really be shifted down. Sorry, I should, let me just make sure that this is somewhere here. Yeah. Okay. So this is, let's call this up. and this is down, and this is strange. Okay, so this is the fundamental, and of course, this is the, this has, you can start with any of the any of these weights, and then, apply the raising, lowering operators to get to the other ones, right? So this is the weight, this is the weight diagram of the fundamental representation. Can someone tell me what the, yeah, sure, Zabir, go ahead. Do you, what about the, can someone tell me what would the anti-fundamental representation look like? Just your intuition, right?
Upside down triangle.
Sorry? Exactly, yeah, because then everything will be, all the particles will become their antiparticles. So the quantum numbers will get flipped. Okay, so basically this is so what Gell-Mann did was that he conjectured that there were three particles called up quark, down quark, and strange quark, and they had, approximately the same, the same masses. And what he conjectured was that all the strong interaction particles were made out of them. So, for example, if you have a particle which is made out of three quarks, and that, the particle physics made out of these guys, we should have SU3 symmetry. Then if you have three quarks, then, particles which are bound state of three quarks should be in the irreducible representation of 3 cross 3. So if you could work this out, maybe these guys will all have, like, there will be irreducible representations. And so the idea was that they were trying to explain all these new particles which were being found in strong interaction physics. No one could bring order to the particle zoo. And Gell-Mann said that he conjectured that, okay, if there are three quarks, up quark, down quark, and strange quark, this is now called flavor symmetry. And then he found, by doing group theory, he found, say, the 8 representation, the adjoint representation. Well, this is actually not the adjoint because it's got 3. It's 8-dimensional, but it's not the adjoint. So this is called an octet. So the octet looks like this. It's like it looks like a perfect hexagon. So the octet has 2 particles or 2 states in the middle, and then here you have what is called a neutron. Here we have proton. You have gamma particle, gamma plus, gamma minus, and gamma 0 at the center. There's also the lambda particle, and then the I think what are these? And of course, these are all, there should be a pathway. They're related by these, because you move around using the raising and the lowering operators, which are in the root diagram, right? So Gell-Mann worked this out, and voila, he found that all these particles were already present in the experimental data, and they had approximately the same kind of mass. So this was a big, this is the baryon octet. There's another octet which is the adjoint representation. there's another octet called the meson octet. And the meson octet comes from doing Q cross Q bar, or say 3 cross 3 bar. And the mesons are the particles which are exchanged in strong interaction by baryons. Okay, baryons interact with each other by exchanging meson particles, and they are also they also turn out to be bound states of quarks and antiquarks. And then he also found what is known as the decuplet. It's a 10. It's a 10-dimensional irreducible representation of SU3, and it looks like this. There are 4 over here, and then I'm just going to draw the lines first so it becomes easier for me. Sorry. Yeah. And then next we have this, and this. And then we have this and this, and then there are these lines. They all have kind of the hexagonal symmetry. Sorry, this is not very well drawn. But you get the idea, and these are resonance particles, so these are very short-lived, but they live long enough so that they are considered to be particles, not some blip. I mean, there's a way to detect resonant particles when you take some advanced quantum mechanics course. You will learn about that. Those are called resonances. So the resonances, when when Gelman worked this out, of these 10 particles, only 9 were known. Okay, so only 9 were known. So Gelman predicted a 10th particle. Okay. New particle, omega, was predicted. Okay, so this is the SU3 decuplet, or decuplet. Okay, and sure enough, this was found soon afterwards, and Gelman got the Nobel Prize. And since then, group theory has had a huge impact on high energy physics, and and this was even before gauge theory. Group theory has another application which we haven't talked about, which is gauge theory, even before gauge theory became a popular thing. So anyway, I think this is where I'm going to end the class. Tomorrow there will be a special relativity class for those interested. But are there any questions?
So these are analogous to those ladder diagrams?
Yes, yeah. These are analogous to these diagrams, like these, yeah, exactly, the ladder diagrams, yeah. Yeah, you're right, like these diagrams, yeah. They're basically, weight diagrams, because remember that we call this the highest weight state?
Yeah. Right.
Sorry. Right, so these are weight diagrams. That's one way to remember which are the roots and which are the weight diagrams. The weight diagrams are the representations. Okay, any more questions? So this is, by the way, this very famous paper was called the eightfold way. The eightfold way. And because there were prominent presence of octets, and Murray Gell-Mann was an extremely well-read guy, and he had read about He was interested in Buddhism, and he knew about the Eightfold Way of Buddhism, so he called the paper the Eightfold Way. So an unfortunate consequence of this was that there were a lot of pseudoscientific, well, I would say unscientific, pseudo mystical articles written about ideas came forward as inspired by that